Chapter 9 Weight and Balance Control, Commuter Category and Large Aircraft Introduction. This chapter discusses general guidelines and procedures for weighing large fixed-wing aircraft exceeding a takeoff weight of 12,500 pounds. Several examples of center of gravity (CG) determination for various operational aspects of these aircraft are also included. Persons seeking approval for a weight and balance control program for aircraft operated under Title 14 of the Code of Federal Regulations, 14 CFR, Part 91, Subpart K, 121, 125, or 135 should consult with the Flight Standards District Office, FSDO, or Certificate Management Office, CMO, that has jurisdiction in their area. Additional information on weight and balance for large aircraft can be found in Federal Aviation Administration, FAA Advisory Circular, AC 120-27, Aircraft Weight and Balance Control, FAA Type Certificate Data Sheets, TCDS, and the Aircraft Flight and Maintenance Manuals for specific aircraft. Establishing the initial weight of an aircraft prior to being placed into service, each aircraft is weighed in the empty weight and CG location established. New aircraft are normally weighed at the factory and are eligible to be placed into operation without reweighing if the weight and balance records were adjusted for alterations and modifications to the aircraft, such as interior reconfigurations and aircraft transferred from one operator that has an approved weight and balance program to another operator with an approved program does not need to be weighed prior to use by the receiving operator unless more than 36 calendar months have elapsed since the last individual or fleet weighing, or unless some other modification to the aircraft warrants that the aircraft be weighed. Aircraft transferred, purchased, or leased from an operator without an approved weight and balance program, and that have not been modified or have been minimally modified, can be placed into service without being reweighed if the last weighing was accomplished by an acceptable method, for example, manufacturer's instructions or AC 43.13-2, acceptable methods, techniques, and practices, aircraft alterations, within the last 12 calendar months and a weight and balance change record was maintained by the operator. It is potentially unsafe to fail to reweigh an aircraft after it has been modified when weighing large aircraft. Compliance with irrelevant manuals, operations specifications, or management specification is required to ensure that weight and balance requirements specified in the Aircraft Flight Manual, AFM, are met in accordance with approved limits. This provides information to the flight crew that allows the maximum payload to be carried safely. The aircraft should be weighed in still air or an enclosed building after the aircraft has been cleaned. Ensure that the aircraft is in a configuration for weighing with regard to flight controls, unusable fuel, ballast, oil and other operating fluids, and equipment as required by the controlling weight and balance procedure. Large aircraft are not usually raised off the floor on jacks for weighing, they are weighed on ramp-type scales. The scales must be properly calibrated, zeroed, and used in accordance with the manufacturer's instructions. Each scale should be periodically checked for accuracy as recommended in the manufacturer's calibration schedule, either by the manufacturer or by a recognized facility, such as a Civil Department of Weights and Measures. If no manufacturer's schedule is available, the period between calibrations should not exceed 12 months. Determining the empty weight and empty weight CG, EWCG, when the aircraft is properly prepared for weighing, roll it onto the scales, and level it. The weights are measured at 3 weighing points, the 2 main wheel points and the nose wheel point. The empty weight and empty weight CG, EWCG, are determined by using the following steps with the results recorded in the weight and balance record for use in all future weight and balance computations. 1. Determine the moment index of each of the main wheel points by multiplying the net weight, scale reading minus tare weight, in pounds, at these points by the distance from the datum, in inches. Divide these numbers by the appropriate reduction factor. 2. Determine the moment index of the nose wheel weighing point by multiplying its net weight in pounds, by its distance from the datum, in inches. Divide this by the reduction factor. 3. Determine the total weight by adding the net weight of the 3 weighing points and the total moment index by adding the moment indexes of each point. 4. Divide the total moment index by the total weight and multiply the result by the reduction factor. This gives the CG in inches from the datum. CG distance weight is shifted 5. Determine the distance of the CG behind the leading edge of the mean aerodynamic chord, LEMAC, by subtracting the distance between the datum and LEMAC from the distance between the datum and the CG. Figure 9.1.6. Determine the EWCG in percentage of MAC, %MAC, by using the formula in Figure 9.2. Documenting changes to an aircraft's weight and balance. The weight and balance system should include methods by which a complete, current, and continuous record of the weight and CG of each aircraft is maintained, such as a log ledger, or other equivalent electronic means. Alterations and changes affecting the weight and/or balance of the aircraft should be recorded in this log. Changes in the weight or location of weight in or on the aircraft should be recorded whenever the weight changes at or exceeds the weights listed in Figure 9.3. Determining the loaded CG of the airplane in % Mach. A loading schedule is used to document compliance with the certificated weight and balance limitations contained in the manufacturer's AFM and weight and balance manual. The basic operating weight, BOW, and the operating index are entered into a loading schedule like the one in Figure 9.4, and the variables for a specific flight are entered as appropriate to determine the loaded weight and CG. Use the data in this example: basic operating weight, 105,500 pounds, basic operating index, total moment /1,000, 98,837.0 Mach, 180.9 in Lmach, 860.5. Figure 9.5 illustrates passenger, cargo, and fuel loading tables. Using these tables, determine the moment indexes for the passengers, PAX, cargo, and fuel. The airplane is loaded in this way: passengers, nominal weight, 170 pounds each, forward compartment, 18 aft compartment, 95 cargo, forward hold, 1,500 pounds aft hold, 2,500 pounds fuel, tanks 1 and 3, 10,500 pounds each, tank 2, 28,000 pounds. The formula in Figure 9.6 can be used to determine the location of the CG in inches after the datum. Determine the distance from the CG to the Lmach by subtracting the distance between the datum and Lmach from the distance between the datum and the CG. Figure 9.7. The location of the CG in % Mach must be known in order to set the stabilizer trim takeoff. Figure 9.8. Operational empty weight, OEW. Operational empty weight, OEW, is the basic empty weight or FL at empty weight plus operational items. The operator has two choices for maintaining OU. The loading schedule may be utilized to compute the operational weight and balance of an individual aircraft, or the operator may choose to establish fleet empty weights for a fleet or group of aircraft. Re-establishing the OU. The OU and CG position of each aircraft should be re-established at the reweighing. In addition, it should be re-established through calculation whenever the cumulative change to the weight and balance log is more than plus or minus 1/2%, 0.5%, of the maximum landing weight, or whenever the cumulative change in the CG position exceeds 1/2%, 0.5%, of the Mach. In the case of rotorcraft and aircraft that do not have a Mach-based CG envelope, for example, canard-equipped airplane, whenever the cumulative change in the CG position exceeds 1/2%, 0.5%, of the total CG range, the weight and balance should be re-established. When re-establishing the aircraft OU between reweighing periods, the weight changes may be computed provided the weight and CG location of the modifications are known; otherwise, the aircraft must be reweighed. Fleet operating empty weights, FOEW. An operator may choose to use one weight for a fleet or group of aircraft if the weight and CG of each aircraft is within the limits stated above for establishment of OU. When the cumulative changes to an aircraft weight and balance log exceed the weight or CG limits for the established fleet weight, the empty weight for that aircraft should be re-established. This may be done by moving the aircraft to another group, or re-establishing new fleet operating empty weights, FOEs. Onboard aircraft weighing system. Some large transport airplanes have an onboard aircraft weighing system, a BAWS, that, when the aircraft is on the ground, gives the flight crew a continuous indication of the aircraft total weight and the location of the CG in % Mach. Procedures are required to ensure the onboard weight and balance system equipment is periodically calibrated in accordance with the manufacturer's instructions. An operator may use an onboard weight and balance system to measure an aircraft's weight and balance as a primary means to dispatch an aircraft, provided the FAA has certified the system and approved the system for use in an operator's weight and balance control program. As part of the approval process, the onboard weight and balance system must maintain its certificated accuracy. The accuracy demonstration test is provided in the maintenance manual portion of the Supplemental Type Certificate, STC, or Type Certificate of the onboard weight and balance system. The system consists of strain sensing transducers in each main wheel and nose wheel axle, a weight and balance computer, and indicators that show the gross weight, the CG location in % Mach, and an indicator of the ground attitude of the aircraft. The strain sensors measure the amount each axle deflects CTS and sends this data into the computer, where signals from all of the transducers and the ground attitude sensor are integrated. The results are displayed on the indicators for the flight crew. Using an onboard weight and balance system does not relieve an operator from the requirement to complete and maintain a load manifest. Determining the correct stabilizer trim setting. It is important before takeoff to set the stabilizer trim for the existing CG location. There are two ways the stabilizer trim setting systems may be calibrated: in % Mach and in units airplane nose up, ANU. If the stabilizer trim is calibrated in %Mach, determine the CG location in %Mach as has just been described, then set the stabilizer trim on the percentage figure thus determined. Some aircraft give the stabilizer trim setting in units of ANU that correspond with the location of the CG in %Mach. When preparing for takeoff in an aircraft equipped with this system, first determine the CG in %Mach in the way described above, then refer to the stabilizer trim setting chart on the takeoff performance page of the pertinent AFM. Figure 9.9 is an excerpt from the AFM chart on the takeoff performance of a Boeing 737. Consider an airplane with these specifications: CG location, station 635.7 Lee Mach, station 625 Mach, 134.0 and 1. Determine the distance from the CG to the Lee Mach by using the formula in figure 9.10. 2. Determine the location of the CG in %Mach by using the formula found in figure 9.11. Refer to figure 9.9 for all flap settings and a CG located at 8% Mach. The stabilizer setting is 73/4 units ANU. Determining CG changes caused by modifying the cargo, since large aircraft can carry substantial cargo, adding, subtracting, or moving any of the cargo from one hold to another can cause large shifts in the CG. Effects of loading or offloading cargo. Both the weight and CG of an aircraft are changed when cargo is loaded or offloaded. In the following example, the new weight and CG are calculated after 2,500 pounds of cargo is offloaded from the forward cargo hold. Aircraft specifications are: loaded weight, 90,000 pounds; loaded CG, 22.5% Mach; weight change, 2,500 pounds; forward cargo hold centroid, station 352.1 Mach, 141.5 in Lee Mach, station 549.131. Determine the CG location in inches from the datum before the cargo is removed. Do this by first determining the distance of the CG aft of the Lee Mach. Figure 9.12. 2. Determine the distance between the CG and the datum by adding the CG in inches aft of Lee Mach to the distance from the datum to Lee Mach. Figure 9.13. 3. Determine the moment/1,000 for the original weight. Figure 9.14. 4. Determine the new weight and new CG by first determining the moment/1,000 of the removed weight. Multiply the weight removed, 2,500 pounds, by the centroid of the forward cargo hold, 352.1 inches, and then divide the result by 1,000. Figure 9.15. 5. Subtract the removed weight from the original weight and subtract the moment/1,000 of the removed weight from the original moment/1,000. Figure 9.16. 6. Determine the location of the new CG by dividing the total moment/1,000 by the total weight and multiplying this by the reduction factor of 1,000. Figure 9.17. 7. Convert the new CG location to %Mach. First, determine the distance between the CG location and Lee Mach. Figure 9.18. 8. Then, determine the new CG in %Mach. Figure 9.19. Loading 3,000 pounds of cargo into the forward cargo hold moves the CG forward 5.51 inches, from 27.12% Mach to 21.59% Mach. Effects of shifting cargo from one hold to another. When cargo is shifted from one cargo hold to another, the CG changes, but the total weight of the aircraft remains the same. For example, use the following data: loaded weight, 90,000 pounds; loaded CG, station 580.97, 22.5% Mach; forward cargo hold centroid, station 352; aft cargo hold centroid, station 724.9 Mach, 141.5 in Lee Mach, station 549. To determine the change in CG, delta CG, caused by shifting 2,500 pounds of cargo from the forward cargo hold to the aft cargo hold, use the formula in figure 9.20. Since the weight was shifted aft, the CG moved aft and the CG change is positive. If the shift were forward, the CG change would be negative. Before the cargo was shifted, the CG was located at station 580.97, which is 22.5% of Mach. The CG moved aft 10.36 inches, so the new CG is found using the formula from figure 9.21. Convert the location of the CG in inches aft of the datum to %Mach by using the formula in figure 9.22. The new CG in %Mach caused by shifting the cargo is the sum of the old CG plus the change in CG. Figure 9.23. Some AFMs locate the CG relative to an index point rather than the datum or the Mach. An index point is a location specified by the aircraft manufacturer from which arms used in weight and balance computations are measured. Arms measured from the index point are called index arms, and objects ahead of the index point have negative index arms, while those behind the index point have positive index arms. Use the same data as in the previous example, except for these changes. Loaded CG, index arm of 0.97, which is 22.5% of Mach index point. Fuselage station 580.0 forward cargo hold centroid, minus 227.9 index arm aft cargo hold centroid, plus 144.9 index arm Mach, 141.5 in lee Mach, minus 30.87 index arm. The weight was shifted 372.8 inches, minus 227.9 plus delta equals plus 144.9, delta equals 372.8. The change in CG can be calculated by using this formula found in figure 924. Since the weight was shifted aft, the CG moved aft and the CG change is positive. If the shift were forward, the CG change would be negative. Before the cargo was shifted, the CG was located at 0.97 index arm, which is 22.5% Mach. The CG moved aft 10.36 inches, and the new CG is shown using the formula in figure 925. The change in the CG in % Mach is determined by using the formula in figure 926. The new CG in % Mach is the sum of the old CG plus the change in CG. Figure 927. Notice that the new CG is in the same location whether the distances are measured from the datum or from the index point. Determining cargo pallet loads and floor loading limits. Each cargo hold has a structural floor loading limit based on the weight of the load and the area over which this weight is distributed. To determine the maximum weight of a loaded cargo pallet that can be carried in a cargo hold, divide its total weight, which includes the weight of the empty pallet and its tie-down devices, by its area in square feet. This load per square foot must be equal to or less than the floor load limit. In this example, determine the maximum load that can be placed on this pallet without exceeding the floor loading limit. Pallet dimensions: 36 by 48. An empty pallet weight, 47 pounds. Tie-down devices, 33 pounds. Floor load limit, 169 pounds per square foot. The pallet has an area of 36 inches, 3 feet, by 48 inches, 4 feet, which equals 12 square feet, and the floor has a load limit of 169 pounds per square foot. Therefore, the total weight of the loaded pallet can be 169 times 12 equals 2,028 pounds. Subtracting the weight of the pallet and the tie-down devices gives an allowable load of 1,948 pounds, 2,028-47 plus 33. Determine the floor loading limit that is needed to carry a loaded cargo pallet having the following dimensions and weights. Pallet dimensions: 48.5 by 33.5 in pallet weight, 44 pounds. Tie-down devices, 27 pounds. Cargo weight, 786.5 pounds. First, determine the number of square feet of pallet area as shown in figure 928. Then, determine the total weight of the loaded pallet, 44.0 pounds. Tie-down devices, 27.0 pounds. Cargo, 786.5 pounds. Total, 857.5 pounds. Determine the load imposed on the floor by the loaded pallet. Figure 929, the floor must have a minimum loading limit of 76 pounds per square foot. Determining the maximum amount of payload that can be carried. The primary function of a transport or cargo aircraft is to carry payload, which is the portion of the useful load, passengers, or cargo that produces revenue. To determine the maximum amount of payload that can be carried, both the maximum limits for the aircraft and the trip limits imposed by the particular trip must be considered. In each of the following steps, the trip limit must be less than the maximum limit. If it is not, the maximum limit must be used. These are the specifications for the aircraft in this example. Basic operating weight, BOW, 100,500 pounds. Maximum zero fuel weight, 138,000 pounds. Maximum landing weight, 142,000 pounds. Maximum takeoff weight, 184,200 pounds. Fuel tank load, 54,000 pounds. Estimated fuel burn en route, 40,000 pounds. 1. Compute the maximum takeoff weight for this trip. This is the maximum landing weight plus the trip fuel. Figure 932. The trip limit is lower than the maximum takeoff weight, so it is used to determine the zero fuel weight. Figure 931, 3. The trip limit is again lower than the maximum takeoff weight, so use it to compute the maximum payload for this trip. Figure 932, under these conditions, 27,500 pounds of payload may be carried. Determining the landing weight. It is important to know the landing weight of the aircraft in order to set up the landing parameters and to be certain the aircraft is able to land safely at the intended destination. In this example of a 4-engine turboprop airplane, determine the airplane weight at the end of 4.0 hours of cruise under these conditions. Takeoff weight, 140,000 pounds. Pressure altitude during cruise, 16,000 feet. Ambient temperature during cruise, -32 degrees Celsius. Fuel burn during descent and landing, 1,350 pounds. Refer to the U.S. Standard Atmosphere Table in Figure 933 and the Gross Weight Table in Figure 934 when completing the following steps. 1. Use the U.S. Standard Atmosphere Table to determine the standard temperature for 16,000 feet, minus 16.7 degrees Celsius. 2. The ambient temperature is minus 32 degrees Celsius, which is a deviation from standard of 15.3 degrees Celsius. Minus 32 degrees, minus 16.7 degrees, equals minus 15.3 degrees. It is below standard. 3. In the gross weight table, follow the vertical line representing 140,000 pounds gross weight upward until it intersects the diagonal line for 16,000 feet pressure altitude. 4. From this intersection, draw a horizontal line to the left to the temperature deviation index, 0 degrees Celsius deviation. 5. Draw a diagonal line parallel to the dashed lines for below standard from the intersection of the horizontal line and the temperature deviation index. 6. Draw a vertical line upward from the 15.3 degrees Celsius temperature deviation from standard. 7. Draw a horizontal line to the left from the intersection of the below standard diagonal and the 15.3 degrees Celsius temperature deviation vertical line. This line crosses the fuel flow 100 pounds per hour per engine index at 11.35 and indicates that each of the 4 engines burns 1,135, 100 times 11.35, pounds of fuel per hour. The total fuel burn for the 4-hour cruise is shown in Figure 935. The airplane gross weight was 140,000 pounds at takeoff with 18,160 pounds of fuel burned during cruise and 1,350 pounds burned during the approach and landing phase. This leaves a landing weight of 140,000, 18,160 plus 1,350, equals 120,490 pounds. Determining fuel dump time in minutes. Most large aircraft are approved for a greater weight for takeoff than for landing. To make it possible for them to return to landing soon after takeoff, a fuel jettison system is sometimes installed. It is important in an emergency situation that the flight crew be able to dump enough fuel to lower the weight to its allowed landing weight. This is done by timing the dumping process. In this example, the aircraft has 2 engines operating and these specifications apply: cruise weight, 171,000 pounds, maximum landing weight, 142,500 pounds, time from start of dump to landing, 19 minutes, average fuel flow during dumping and descent, 3,170 pounds per hour / eng fuel dump rate, 2,300 pounds / minute. To calculate the fuel dump time in minutes. 1. Determine the amount of weight the aircraft must lose to reach the maximum allowable landing weight. Figure 936. 2. Determine the amount of fuel burned from the beginning of the dump to touchdown. Figure 937, for both engines, this is 52.83 times 2 equals 105.66 pounds / minute. The engines burn 105.66 pounds of fuel per minute for 19 minutes, the duration of the dump, which calculates to 2007.54 pounds of fuel burned between the beginning of the dump and touchdown. 3. Determine the amount of fuel needed to dump by subtracting the amount of fuel burned during the dump from the required weight reduction. Figure 938. 4. Determine the time needed to dump this amount of fuel by dividing the number of pounds of fuel to dump by the dump rate. Figure 939, weight and balance of commuter category airplanes. The Beech 1900 is a typical commuter category airplane that can be configured to carry passengers or cargo. Figure 940 shows the loading data of this type of airplane and the passenger configuration determining the loaded weight and CG. As this airplane is prepared for flight, a manifest is prepared. Figure 941. 1. The crew weight and the weight of each passenger is entered into the manifest. The moment /100 for each occupant is determined by multiplying the weight by the arm and dividing by 100. This data is available in the AFM and is shown in the weight and moments, occupants table. Figure 942. 2. The weight of the baggage in each compartment used is entered with its moment /100. This is determined in the weights and moments, baggage table. Figure 943. 3. Determine the weight of the fuel. Jet fuel has a nominal specific gravity at plus 15 degrees Celsius of 0.812 and weighs 6.8 pounds per gallon, but at plus 25 degrees Celsius, according to the density variation of aviation fuel chart, figure 944, it weighs 6.75 pounds /gal. Using this chart, determine the weights and moments /100 for 390 gallons of jet fuel by interpolating between those for 6.7 pounds /gal and 6.8 pounds /gal. The 390 gallons of fuel at this temperature weighs 2,633 pounds, and its moment index is 7,866 pounds in /100. 4. Add all of the weights and all of the moment indexes. Divide the total moment index by the total weight, and multiply this by the reduction factor of 100. The total weight is 14,729 pounds, the total moment index is 43,139 pounds / 100. The CG is located at fuselage station 292.9. Figure 945-5. Check to determine that the CG is within limits for this weight. Refer to the weight and balance diagram. Figure 946. Draw a horizontal line across the envelope at 14,729 pounds of weight and a vertical line from the CG of 292.9 inches after the datum. These lines cross inside the envelope, verifying the CG is within limits for this weight. Determining the changes in CG when passengers are shifted using the loaded weight and CG of the Beech 1900, calculate the change in CG when the passengers in rows 1 and 2 are moved to rows 8 and 9. Figure 947. Note that there is no weight change, but the moment index has been increased by 1,155 pound-inches / 100 to 44,294. The new CG is at fuselage station 300.7. Figure 948. This type of problem is usually solved by using the following two formulas. The total amount of weight shifted is 550 pounds, 300 plus 250, and both rows of passengers have moved aft by 210 inches, 410 to 200 and 440 to 230. The CG has been shifted aft by 7.8 inches, and the new CG is at station 300.7. Figure 949. In a large cabin aircraft with high-density seating such as the B737-800, the operator must account for the seating of passengers in the cabin, figure 950. If assigned seating is used to determine passenger location, the operator must implement procedures to ensure the assignment of passenger seating is incorporated into the loading procedure. It is recommended that the operator take into account the possibility that some passengers may not sit in their assigned seats. If the actual seating location of each passenger is not known, the operator may assume that all passengers are seated uniformly throughout the cabin or a specified subsection of the cabin. Reasonable assumptions can be made about the manner in which people distribute themselves throughout the cabin. For example, window seats are occupied first, followed by aisle seats, followed by the remaining seats, window aisle remaining seating. Both forward and rear loading conditions should be considered. The passengers may fill up the window, aisle, and remaining seats from the front of the aircraft to the back, or the back to the front. If necessary, the operator may divide the passenger cabin into subsections or zones and manage the loading of each zone individually. It can be assumed that passengers will be sitting uniformly throughout each zone. Another consideration is the in-flight movement of passengers, crew, and equipment. It is assumed that all passengers, crew, and equipment are secured when the aircraft is in the takeoff or landing configuration. Standard operating procedures should be taken into account. Examples of items that can move during flight are flight deck crew members moving to the lavatory, flight attendants moving throughout the cabin, service carts moving throughout the cabin, passengers moving throughout the cabin, passengers moving to the lavatory. Determining changes in weight and CG when the aircraft is operated in its cargo configuration. To determine changes in weight and CG when the aircraft is operated in its cargo configuration, the Beech 1900 is used as an example. Figure 951 illustrates the airplane configuration. Notice that the arm of each cargo section is the centroid of that section. The flight manifest of the Beech 1900 in the cargo configuration is illustrated in Figure 952. The bow includes the pilots and their baggage, and then there is no separate item for them. At the standard temperature of 15 degrees Celsius, the fuel weighs 6.8 pounds per gallon. Refer to Figure 945 to determine the weight and moment index of 370 gallons of jet fuel. The CG under these loading conditions is located at station 296.2. Determining the CG shift when cargo is moved from one section to another. To calculate the CG when cargo is shifted from one section to another, use the formula found in Figure 953. If the cargo is moved forward, the CG is subtracted from the original CG. If the cargo is shifted aft, add the CG to the original. Determining the CG shift when cargo is added or removed. To calculate the CG when cargo is added or removed, add or subtract the weight and moment index of the affected cargo to the original loading chart. Determine the new CG by dividing the new moment index by the new total weight, and multiply this by the reduction factor. Figure 954, determining which limits are exceeded when preparing an aircraft for flight. Consider all parameters and check to determine that no limits have been exceeded. Consider the parameters below, and determine which limit, if any, has been exceeded. The aircraft in this example has a basic empty weight of 9,005 pounds and a moment index of 25,934 pound-inches/100. The crew weight is 340 pounds and its moment/100 is 439. The passengers and baggage have a weight of 3,950 pounds and a moment/100 of 13,221. The fuel is computed at 6.8 pounds/gal. The ramp load is 340 gallons or 2,312 pounds. Fuel used for start and taxi is 20 gallons, or 136 pounds. Fuel remaining at landing is 100 gallons, or 680 pounds. Maximum takeoff weight is 16,600 pounds. Maximum zero fuel weight is 14,000 pounds. Maximum landing weight is 16,000 pounds. Take these steps to determine which limit, if any, is exceeded. 1. Determine the zero fuel weight, which is the weight of the aircraft with all of the useful load except the fuel on board. Figure 955, the zero fuel weight of 13,295 pounds is less than the maximum of 14,000 pounds, so this parameter is acceptable. 2. Determine the takeoff weight in CG. The takeoff weight is the zero fuel weight plus the weight of the ramp load of fuel minus the weight of the fuel used for start and taxi. The takeoff CG is the moment/100 divided by the weight, and then the result multiplied by 100. The takeoff weight of 15,471 pounds is below the maximum takeoff weight of 16,600 pounds, and a check of the weight and balance diagram shows that the CG at station 298.0 is also within limits. Figure 956, 3. Determine the landing weight in CG. This is the zero fuel weight plus the weight of fuel at landing. Figure 957, the landing weight of 13,975 pounds is less than the maximum landing weight of 14,000 to 16,000 pounds. According to the weight and balance diagram, the landing CG at station 297.5 is also within limits.